Hi everyone. So in today's video, we are going to go over this paper, Emergent and Predictable Memorization in Large Language Models. The authors are Stella Biderman, U.S. VSN Sai Prashant, Mintang Sutarika, Haley Sherlikoff, Quentin Anthony, Shivanshu Purohit, and Edward Raff. I'm really sorry if I mispronounced any of those names. So all of them are from Eleutheria and also, some one of them is from Pooja and Hamilton, and they have other affiliations as well. Alright, so jump into the abstract. Memorization or the tendency of LLMs to output entire sequences from their training data verbatim is a key concern for safely deploying LLMs. In particular, it is vital to minimize the model's memorization of sensitive data points. So, data points containing personal identifiable information. The prevalence of such undesirable memorization can pose issues for model trainers and may even require discarding an otherwise functional model. We therefore seek to predict which sequences will be memorized before a large language model's full train time by extrapolating the memorization behavior of lower compute trial runs. We measure memorization of the Python model suite and plot scaling laws for forecasting memorization, allowing us to provide equi-compute recommendations to maximize the reliability of such predictions. We additionally provide further novel discoveries on the distribution of memorization, of course, across models and data, and they release all the code. All right. So, for the introduction, recent NLP research in generative tasks has largely been driven by two findings. One is that the transformer architecture performs well, and secondly, increasing the scale of transformer architecture leads to improved performance. So, as the name goes, go bigger. In addition to these benefits, transformers are a general and multi-purpose architecture that have achieved state-of-the-art results outside of NLP on diverse tasks such as text-to-image synthesis, code generation, routine folding, and many more. Despite their widespread success and increasing use, the internal workings of Transformer are poorly understood, and research into how a given model learns and internally represents data has the potential to affect a broad range of high impact applications. Alright, so memorization in LLMs. In particular, the demonstrated capacity and ability of these LLMs to memorize data has become a significant concern. The most obvious ramification is personal information on otherwise sensitive data being leaked to the public at large and extracted by a bad actor. Although it has not been formally demonstrated in the literature to the best of our knowledge, some forms of memorization are actually beneficial. We want large language models to memorize factual events and details to avoid hallucinating plausible sounding but errant facts to unsuspecting users. So this is one case where memorization is desirable. Despite the extensive literature on memorization in trained models, there are few tools to help practitioners either prevent memorization or detect it early in the model training. So before the advent of transformer-based LLMs, work using differential privacy was popular. However, such methods have been observed to hurt performance during pre-training and are therefore not popular among people who train LLMs. In recent years, the bulk of interventionist work has focused on how removing duplicated samples from the training data set, known as deduplication, can decrease memorization. Importantly, these works focus on memorization on average and cannot be relied on to prevent memorization of specific training examples. So this is the differentiator. So one work introduced an interference time intervention that has 100% success rate at preventing verbatim memorization, but they note that the methodology is easily subverted and does not fulfill the intention behind the memorization, which is tendency of models to learn samples during training and without understanding their underlying meaning. So both of these memorization outcomes can be better studied, tackled, and remediated if there exist tools to predict the memorization of specific data points prior to model training, rather than the macro-level corpus-wide statistics considered by prior work. So they take a first step in this direction by proposing two strategies. So one, making predictions from a smaller model to a larger model, and two, making predictions from a partially trained model of a given size to a fully trained model. So using these small partial model runs to inform large runs is critical. Specifically, these small runs provide a cheap method to inform training behavior for a given corpus rather than training an entire model from scratch. We find that the efficacy of these proposed methods varies with the downstream intended use, depending on whether precision we want something to be memorized, we want to confirm something was memorized or recall, we want something forgotten is most desired. So, based on which one of these you prioritize, your efficacy varies, of course. So, scaling laws and emergent properties. Our approach to prediction and memorization of specific sequences is inspired by the literature on scaling laws. So, due to the substantial cost of training LLMs, it is highly desirable to be able to make predictions about model characteristics before they are actually trained. The literature on scaling laws has been successfully used to inform the decision making of a variety of researchers at model training time by allowing them to generalize the decisions made while investigating smaller models to inform the design of larger models. So instead of like just going and training a 10 billion parameter model, you might make some observations on a 100 million or 1 billion parameter size model and use that also. So while this work on scaling laws does extend to memorization, how memorization evolves during a model training process across a variety of scales has not been studied. More recently, attention has been directed to areas where scaling laws, or at least traditional conceptions of them, fail. In particular, you have these works which study things which are called emergent properties of language models, where some downstream tasks see almost no change in performance as the model size scales until a critical point at which the performance starts to increase rapidly. So you might have a task where unless if the model is smaller than 1 billion, you don't see any gain, but once you hit that spot, then your models sort of start to actually learn things. Our contribution. In this paper, we introduce the question of extrapolating a model's memorization behavior for specific training data points based on evaluations set in relatively low-cost training regimes. These low-cost regimes enable us to abort models without wasting significant compute in the event of undesirable behavior. This includes the typical setting where we extrapolate the qualities of a language model based on large language model based on smaller models, as well as a novel setting where we extrapolate the behavior of fully trained ones based on partially trained models. As far as we are aware, so this is the first paper which does this. Listing their contributions, they introduce the problem of forecasting whether or not a model memorizes a specific training data. The discovery that memorization of a specific training string by LLM is not reliably predicted by either studying smaller ones or partially trained checkpoints unless a sizable fraction of the pre-training corpus is used. And finally, a preliminary analysis of scaling laws for forecasting memorization and recommendation for maximizing forecast reliability. So the rest of the paper is organized in some sections. You have relevant facets of the methodology, then we have the threat model, the choice of pre-trained model, feasibility, and then we have all these sections. So let's just jump into the sections. The first section is their methodology. So memorization is an intuitive concept that for many people stands distinct from good learning in some senses. However, formalizing the intuition presents challenges. So they are following the definition by Carlin et al., which is key extractability. I've covered this paper on this channel. I just recorded that video a few hours ago. So if you want to check that out, you can check it out. So the definition, a string S is said to be key extractable if it exists in the training data and is generated by the language model by prompting with K prior tokens. So if you give the prompt the email address and you get this email ID which was present in the training data, this entire sentence was present in the training data, then this is called 3K extractable, where K is so thus producing an exact copy of the training data. We term accuracy of tokens in the continuation as the memorization score and call a sequence K memorizer K extractable if the memorization score is 1. So you want the scores of the generator to be equal to the ground truth, and this basically gives you a score of how many tokens match, and then if it is 100% matching, you say it is memorized. In addition to K extractability, we evaluate the memorization score, defined as the number of ordered matching tokens between the model's readily decoded sequence and the dataset's true continuation. Right, so this is the definition. Doing a forward pass on a large transformer is relatively expensive, costing about one third the cost of a full gradient update step. Consequently, feeding the full training data through the model for a forward pass would approximately cost one third the amount of compute that training the model did, which is a lot. And doing the full 7 checkpoints that we do come out to a larger compute budget than training the models themselves. So, since this is one third, doing this 7 times is a bit more than training the model twice. So to ensure the computational feasibility, they choose case 32 and evaluate the first 64 tokens from each sequence. And each sequence is a set of 2048 tokens sampled from shuffled documents. And these are their inputs. So this makes sense to do because you can't be uh, looking at predicting. So you can't be looking at memorization and then the entire method which you're using costs more than what your the training cost is. And even if this is a one-time cost and not something which everyone would need to do, this is still a large enough value for people to make optimizations. Alright, so the threat model. Throughout the paper, we assume that an engineer is looking to train a large language model with billions of parameters on a dataset, and that there is a small subset of the dataset that would be undesirable to have the model memorized. The engineer therefore wishes to be able to accurately predict whether or not this will be memorized by the fully trained model by expending a relatively small amount of compute. So, following the literature on scaling laws, the cost of training a model is approximately 6 times the number of parameters times the number of tokens, and that the engineer has a computing budget that allows them to perform substantial testing before performing the full model training run. So this cost is like very popular in literature, but I would assume that these larger companies which own like I guess Llama 2 or stuff like that, they would have had better deals maybe who knows. Now, predicting memorization, we can treat a smaller model's memorization of a sequence or lack thereof as a predictor for the memorization behavior of a larger model. Whether the interested model did memorize a sequence is the ground truth level, and the smaller model's behavior is the prediction. For example, if a smaller model memorized a sequence and the larger model did not, we can think of this case as a false positive. Likewise, if both of them memorize, then this is a true positive. Model not memorizing are negative cases. So I guess this makes sense. The prediction by the smaller model compared against the ground truth allows us to calculate classification metrics like precision and recall. In this case, precision tells us how many of the sequences memorized by the smaller model are also memorized by the larger ones, and recall conveys the percentage of sequence memorized by the larger ones that are also memorized by the smaller one. The same framing can also be applied when analyzing across time. So if you're comparing the first checkpoint to the second and so on. As the engineer's sole concern is to avoid memorization, false negative and false positive have very different impact. So a false positive, that is you have incorrectly predicted that a model will memorize this, results in throwing away a cheap model that could have been fruitfully continued, while a false negative, that is incorrectly predicting that a model will not memorize, results in a costly training that would be undesirable for that would be useless for the engineer because it memorizes something. So they are primarily interested in assessing the recall, and they will tolerate a lower precision if it comes at a cost of high recall. If it comes with a high recall. So now looking at the data set. So at the time of writing, the only publicly available pre-trained LLM scaling suite trained on fully public training data was Eleuther AI's GPT Neo and the Pythia models and Cerebras Systems Cerebras GPT. So all of these suites were trained on the pile. Additionally, they were able to access the roots dataset that the Big Science Workshop's Bloom model was trained on. So of these model suites, they choose Pythia because all Pythia models sort data samples in the same order. The training data differs slightly across the GPT-Neo model. Some Bloom models have 3 partially trained checkpoints. Some Bloom models only have 3 partially trained checkpoints, and the Cerebral GPT models don't provide partially trained checkpoints. So, due to all of these reasons, the Pythia models are the best for their case. So the computational cost of many of these experiments is quite large. Consequently, we are unable to evaluate every partially trained model checkpoint in the Pythia suite. So for most of the example, they choose to evaluate 7 checkpoints spaced evenly throughout training. So these are the different checkpoints which they take. So these are the number of sequences which the model would have seen at that checkpoint. And they use the GPT Neox library for evaluation. Alright, so memorization across scale. By far the most common type of scaling law to study, and indeed the origin itself of the term itself, is looking at how performance for very large models can be predicted based on the smaller ones. So fully trained smaller model variants are independently useful as artifacts and can be applied. Just a second, I think I broke something. I'll be right back. Yeah, so I guess I'm back. Really sorry about that. I don't know what really happened, but my laptop decided to connect to some other Wi-Fi than what my iPad was on, and then the screen casting pro. All right. Uh, Coming back to the point. So, fully trained smaller model variants are independently useful as artifacts and can be applied in resource-constrained environments in place of a larger model. Therefore, so when projecting the characteristics of higher compute model run via scaling studies, training smaller model variants for this purpose is an actively desirable byproduct, in contrast to the alternative of producing many shorter training duration checkpoints of the same single large architecture. So therefore, the first question would be, can an LLM's memorization be predicted across model scales? So to evaluate how productive training smaller models can be, we subset the data to the sequences with a memorization score of 1. Then we look at the correlation between each pair of fully trained model sizes for each which sequences are memorized. Your results are in figure 1. Let's just look at figure 1. Okay, so this is the heat map. I'll bring everything in screen. Yeah. So uh, they report a sharp decline in correlation between which sequences are memorized by a smaller model and the 12 billion model as a gap between the model size increases. Unfortunately, they find that low correlation score causes the set of sequence memorized by smaller model to have very poor predictive power in terms of what will be memorized by the larger model. They also measure precision and recall of fully memorized sequences using smaller models to predict the memorization of 12 billion model. Although the precision is high for all models, they are more interested in the recall. So the recall is incredibly low across the board, with even the 1.4 billion parameter model only achieving a recall of zero point 0.5 when trying to forecast the behavior. The findings suggest that using smaller model runs to forecast the memorization of larger model is not accurate due to the low recall. Practitioners cannot use a small model's lack of memorization of a given sequence as a strong guarantee that a larger model will also not memorize it. Hence, they do not recommend using smaller models for this and seek to provide a setup that grants practitioners more assurances and a better compute trade-off. You can look at the precision values. Even though the precision values are really high, what really matters to them is the recall, of course, for the reasons we discussed above, because you don't really want false negatives because then you'll have a large model which is useless for you. And you can look at the correlations as well. Of course, the diagonally one because models are have high correlation. Like the same thing that will have 100% overlap. But as you look at larger models and the correlation with smaller models, you see that it's pretty low. All right. So now let's look at memorization within training. Can an LLM's memorization behavior be predicted ahead of time? So they wish to determine if by testing memorization behavior after partially completing a training run, an engineer can get a reliable sign about what to do in the future. The analysis in this section is motivated by the finding of Biderman et al. 2023 that location within the training data does not impact whether a particular sequence is memorized. This is the picture by the way. Therefore, we hypothesize that those concerned about the memorization of particular strings would move them early during training. Thus, practitioners could have an early warning signal for detecting memorization. Unfortunately, they continue to find large negative results, but hope that future research with better techniques for predicting memorization might vindicate this idea. If you look at the correlation maps, I guess they're blurred out because I'm using a PDF version imported into OneNote. If you know a better way, do let me know. where I can also preserve annotations and stuff. But like you get the idea, they won't be lying, right? If they found good results, they let us know. In figure 3, we show a correlation heat map between which sequences are memorized by different checkpoints. We only look at memorization of the first 23 million sequences. So you can see again the precision is high, but the recall is low. Alright, so the results largely mirror those in the previous section. The earliest intermediate checkpoint we test do not exhibit high recall that is desirable because you do not want a fully trained model to be used. If you have to train all the while, then effectively like not gaining anything by this exercise. Hence, they observe that intermediate checkpoints is not a silver bullet. It is still the case that my precision remains high throughout, but recall is low. Therefore, in this setting, as well, it is easier to guarantee a sequence will be memorized through such establishments rather than not, since the latter guarantee of non-memorization is more useful. Our focus thus shifts to determining the compute optimal model to train on. Okay, let me. This will be yeah, Ananda. So, right. Let's just continue from the first paragraph on top. So they see that intermediate checkpoints are not a good use case. Therefore, in this setting as well, it is easier to guarantee a sequence will be memorized rather than not, which is what they're more concerned about, since the latter guarantee is more useful. All right. So now let's look at the scaling laws for memorization, I guess. Having established the empirical results, we now examine our results through the lens of computational efficiency, where the aim is to achieve the most reliable results for the least expense. To achieve this, we examine how well models of various sizes and number of training steps predict which sequences will be memorized. This is notable contrast to section 4, where partially trained models are only compared to fully trained models. Thus, the visual weight models with the same size are colored the same. So let's just see what they're doing here. They examine how well models of various sizes and number of training steps predict which sequence will be memorized by the fully trained model. In the previous section, the partially trained model are only compared to the fully trained model of the same size, but here this is not the case. They're only comparing to the 12 billion model, uh, like the memorization in the 12 billion model with intermediate checkpoints and model and different model sizes. So in the overwhelming majority of prior works, including scaling studies targeting memorization, plots of quantities of interest versus computer linear on a log or log-log plot. We find that this is not the case in our setup for both precision and recall. The scaling loss of precision is extremely anomalous. Not only are the plots non-linear, we find the behavior of the 12 billion partially trained model is extremely out of line with the behavior of smaller models. The results for recall are less anomalous, lacking the divergent behavior, but nevertheless do not accord with what the scaling law literature generally expects. Alright, so despite the fact that there is a high level pattern in the scaling law curve for recall, careful look at the data indicates unusual behavior. So in the low compute regime, mm, so when you have lower number of flops, which are of most interest, to minimize the cost of creating a prediction of the behavior before they are trained, they see a consistent pattern of larger models being better than smaller ones for fixed compute. However, as the amount of compute expended scales, this is no longer the case, starting at around 1% of the budget of the fully trained model. Each compute models perform the same regardless of the number of parameters. Starting at around 10%, the fully trained model, the smallest model trained for this compute budget, becomes the best predictor of the memorization in the fully trained model. Uh, so let's look at the plots here. So initially you can see at these early training regimes, the larger models are better, but over time you see, so over time when you uh, are at around 10% of the budget, the smallest model trained for this compute budget becomes the best predictor. So if you look at these points, uh, the red circles are, I guess, this is what they're alluding to. So these points. despite being the smaller ones, are dominating. Now, emergent memorization. We also see evidence of emergent or semi-emergent behavior. In the literature on emergent behavior in LLMs, the term refers to when a large model's performance on a task is substantially different from what we would get by extrapolating the curves. Often, but not always, this occurs when performance goes from near zero to meaningful. While in their situation, this is not totally analogous. One can similarly consider emergent memorization to occur when data is memorized by large models, which cannot be predicted based on memorization behavior of smaller ones. So, since by definition emergent behavior implies that the smaller scale model behaviors are qualitatively different, this can pose challenges for traditional scaling laws or extrapolating model behavior to models order of magnitude larger. As a result, this suggests that it is an important area to study and explore for future work. Finally, a takeaway for engineers. As discussed in section 2.2, the primary point of interest in engineers is to predict the behavior of large language model before it is trained. Such prediction should be grounded in low cost regime. They find the case where high recall is required. Ask a Alright, so not jump sentences. Such prediction should be grounded in low cost regimes such as the behavior of trained test models that are at least an order of magnitude smaller than the target model. They find that for cases where high recall is required, the scaling laws define what size of model should be trained at a given compute budget. In compute regimes less than two orders of magnitude below the final training size, they find that holding the compute budget fixed is desirable to use the smallest model trained on no more than the final one's total token count as possible. And to front load the data seen by the smaller model with sequences, whose memorization would be undesirable in order to include them in this prediction. So the smaller model can give you some sort of prediction for this. Alright, there's a correction as well. So, due to an error in the analysis code, an earlier draft reported a substantially higher recall. This draft corrects those numbers. Alright. Limitations. So, are we measuring the correct thing? This is unclear if so the first thing would be it is unclear if this is the best definition because this is a very hard definition. There might be close by terms which are one token of and so on. Thus is generalized. So this is done in the Pythia suite, but would this generalize to models trained with different hyperparameters? They validate the experiments with replications of reduplicated Pythia models, but no other model suite is replicate capable of replicating this analysis because of lack of checkpoints and so on, which they mention at the top. What about the data content? So our work does not take the actual content of the training data into account. They are looking at predicting the memorization based on what the smaller models memorize. Future work could look at using the properties of the training text as a whole. So, conclusion, they propose a novel setting for forecasting model memorization prior to train time while minimizing the compute required to make this forecast. We present analysis on two most natural setups for extrapolation using fully trained small models and partially trained checkpoints of the final model to compare and predict memorization. We find that using much smaller model is not viable and then partial checkpoints of an existing model are similarly ineffective predictors of the final memorization. They derive scaling laws to find optimal EQ compute predictor and are able to provide recommendation based on this law. And they hope that this can be used for future works as well as for engineers who are trying to avoid this sort of memorization. Then they have acknowledgements and disclosures for funding. All right. Do they have an appendix as well? Let's just see if there are any interesting things there. Um, they are also they've shown plots for the deduplicated case, and then you have like the plot for all the models. What's this first section about? Robustness with thresholding criteria. Okay, so memorization score of one uh, is what is required for it to be high, like considered as memorized. In this case, we are like looking at how the memory sequences look. So if you look at the distribution of memorization scores, we see In their case, this is what they consider, and you see the memorization scores sharply decline, decline in exponential sort of way, but then it has a peak. Their assumption was that this memorization rate would be based on model size. This would be potentially problematic for the study as the 32 token memorized sequence could dominate the set of memorized sequences. However, upon examining the distribution, it was immediately clear that this cannot be the case. So there is a spike at score 1, exponential distribution or thin-tailed distribution, and while they would have a spike at score 1, it is not possible for them to have such a large spike. The effect shown in figure 5 can only occur in thin-tailed distributions such as the power law distribution. So this is a good sign for their analysis as it means that the typical memorized data point in fact has a much larger number of memorized tokens than the 32 token threshold they were worried about. All right, so I guess this is it. I'll be covering a bunch more memorization papers pretty like in the near future. If you like such videos, do let me know if there are any other videos I should go over. Thank you guys for joining in. Hope to see you again next time as well.